Good morning. My name is Rasool Attar. I have been the senior project engineer for the project. I just want to go a little bit over the foundation construction. First of all, I have to thank the NJPE Society for giving me this opportunity to discuss something about the portion or section of this big project, $1.5 billion project. Before going through the foundation stuff like that, let me just explain, as James mentioned before, from the get-go for this project, we have to develop the control checklist. We had to extract from over 4,000 pages of the RPW, which was the specification for the whole project, control checklist for every segment of the project, whether it was the concrete placement, rebar installation, structural steel, what have you. So we developed more than 110 detail of this control checklist, and we had to send it to the EOR, the design firm, to take a look at it. If they need to add something or delete something, we have to finalize it, and then he would stamp it. Then we had to use this one throughout the whole project. At one point, we had the 35 inspector basically on the project locally, and 38 inspector throughout 7 different states for the construction of this big project. So for this segment, I have to explain about the over 200 drill shaft, which was exactly 214 drill shaft that we installed for this project, which basically ranges from 4.5 to 9.5 feet in diameter. There's a steel structure, steel casing that remains for the service life of this project. Other than this drill shaft, we did have for the retaining wall and the abutment on both sides, New York and New Jersey, 1,174 basically conical pipe pile, which was basically 12 feet to 25 feet in length in New Jersey, and 35 to 55 feet in length in New York. It was 20 inch in diameter and 3/8 of an inch thickness. That was just the retaining wall and pipe pile for the abutment and the retaining wall. Then on top of that, since on the New York side, the rock foundation was lower than New York, New Jersey, basically between 45 to 55 feet in depth, we had to do some type of strengthening of the wetland. So for that reason, we went over 1,684 timber pile, which is 12 inch in diameter and between 45 to 50 feet long, to support the access to New York approach. On top of that, we had actually a fender system in front of the New Jersey tower of the bridge, 35 of them, which is 36 inch in diameter, 1 inch thick, and it would go to 45 to 55 feet depth. Now, all of this 214 drill shaft that we had for the project was integral part of the drill shaft as well as pier column, with the exception of the tower footings, which was 24 of them. Each tower footing contained 6 drill shaft, 9.5 feet in the diameter, and of course it was not part of the integral part of the tower. It was part of the big foundation, which was over 2,000 cubic yard of concrete, which Scott is going to talk about it later on in his segment. Now, when we wanted to do the drill shaft, we had to actually use this crane as well as the vibrating hammer to drive this casing into the ground, and we would keep 5 feet of soil plug before we reach into the weathered or the competent rock. Once we go that place, then we would flood the the casing, and we would just go through the rock, and we would make 2 times the diameter of the drill shaft deep into the rock, and we would provide the rock socket. Next slide, please. Before we get into the rock, of course, we would look at the boring rock as well as the resistance of driving the casing into the ground. We would know that we would getting close, and also with the extraction of the spoil from the drill shaft, we would get notice that this is getting close to the weather as well as competent rock. Once we go there, we just drive and go through the rock and make a rock socket. After the rock socket is removed and everything is done, we have to basically use the testing for said basically shaft inspection devices that we would send it down there to have 15 readings. 8 readings according to spec supposed to show half an inch, less than half an inch of sediment after the actually airlifting and cleaning out the way at the bottom of the rock socket. Once that one is done, with the actually inspection of EOR for the geotechnical from the designer, us, KSE, Port Authority, as well as the contractor, we would validify the cleanness of the drill shaft as well as the rock socket, and then after that they would bring the rebar cage, which for all of these rebar cages have been fabricated in Port Ivory, which is on the approach side of the New York approach. Next slide, please. Actually, the rebar cage was made out of the black rebar, basically, and as you can see, we had the cage right, which is stabilizing all the rebars. On the perimeter of this rebar cage, we have provided every 1 foot, 1.5 inch steel pipe, which is plugged at the end of it. So these are acting to use for the CSL testing, cross-hole sonic logging, after we place concrete in the drill shaft. So once they put the cage in, inside the steel casing, we put centralizer to make sure that it is centralized inside the casing, basically. And then we use the tremie concrete with the bucket as well as the pump concrete, and we put the tremie concrete. Once the concrete is come up, of course, at the top portion of the rebar cage on the drill shaft, we had to connect the black bar to the epoxy or galvanized bar, which is going to be connecting to the rebar cage of the pier column. As I said, these are all integral part, basically. So after the completion of the drill shaft concreting, we had to wait 96 hours. Then we would test through this 1.5 inch diameter steel pipe around the drill shaft. We send the devices for the basically cross-hole sonic logging to find out the integrity of the concrete of the drill shaft. Thank God for the whole project. The concrete was in such a way that we did not have any problem for the basically remediation of the concrete. Next slide, please. Now, on top of the drill shaft, as I said, of course, once we bring all the concrete, it's going to combine with the water which was actually inside the shaft. So the latence comes up, and we still keep pouring until it overflow from the top of the shaft. After it dries out, we have to bush hammer it and make sure everything is clean. And then on top of that one, we connect the rebar cage of the pier column to the rebar cage of the drill shaft with the lantern couplers. And of course, we have to make sure that we put everything, the tolerances, everything is taken care of, measured basically. And then we use the EFCO form for the pier column. Of course, as you may notice that because of the slope of the approaches, 4% slope, the size and the length of this pier column as well as the diameter is different. We had from 4 feet to 9 feet in diameter, 19 feet to 115 in height. And for that one, we pour the pier column from 1 lift to up to 3 lifts. So again, once we lift, we put the pier column first lift, and then we had to wait until the thing was completely done, and then we had to bush hammer on top of it, and we built the second form and then poured the second lift as well. So up to 3 lift we used for the basically pier column. Once that pier column is completely done, we had to put the formwork for the pier cap, which was basically from 7 feet wide to 50 feet long. The pier cap alone would take between 100 to 200 yards of concrete. And of course, we had to check constantly the tolerances and all the size and everything for the pier column, pier caps, and everything. So then, of course, I have to mention the fact that through the drill shaft, we would different location, we would have to bring the lighting protection, which comes all the way from drill shaft, goes to the pier column, go to the pier cap for lighting protection, basically. Next, please. Next slide. And now, as I said, placement of concrete, as I said, mentioning that between the 1 to 3 lift, we had to do it for the different stages for the pier column as well as the pier cap. Now, I have to tell you about the expansion joint of the whole project. This project was done in such a way that it would act as a simple support for the dead load, but the basically continuous for the live load. Throughout the whole project, we had 11 basically 11 joint, 11 modular expansion joint, which was 2 in New York, 2 in New Jersey on the basically west side, and then 3 and 4 repeatedly and respectively on the New Jersey on the west as well as east face. Now, next slide, please. I have to mention something about the diaphragm. We had for the diaphragm between all this pier column, we did have the more than 397 girder, concrete, pre-stressed, precast girder, which was coming and fabricating in the Crosona, Pennsylvania, would haul to the job site. These are the 110-ton weight, 8 feet in height, and 175 feet in length. They would come sit on top of the pier cap, and then it would embedded into the bunch of very complicated diaphragm. The diaphragm that contains and combine these girders on top of the pier cap was between 15 to 18,000 pounds of epoxy rebar. And for the placement of the concrete in that area, we had to use 3 different types of concrete for the diaphragm. This was actually integral part of that one. Of course, we did have for that area, we did have basically what you call it, embedded cast in place, basically concrete, and the as I mentioned before, they have three different type of mix design for that one. In that area, we had to provide a small hinge, concrete hinge, which was reducing the maintenance. There was no bearing on that area where we had those humongous diaphragm. So it was like a very long, a very small piece of the basically concrete hinge that was provided. Now, the deck on the approaches was actually precast from the Prosano, the Pennsylvania, and was brought to the project site. We have basically 174,000 square feet of 4-inch thick precast panel for the approaches, and 9-inch panel, which was for the main span, which was made out of the lightweight concrete that Scott is going to go over it on top of that one. I have to mention by saying that one that all this location for different pieces of this bridge that come, it was coming from 12 different locations in 7 different states. So like Unistress was providing the lightweight slab for the main span, which was 120 pounds per cubic feet for the lightweight. So that was placed 4-inch, and then on top of that we had 6 inches of cast in place concrete for the approaches, and of course for the main span they had PPC that Scott is going to go over it. Next slide, please. Now, on the New York approach of Goethals Bridge, the existing one was the railroad bridge, which was having like about 5 span and the concrete pier as well as a structural steel railroad bridge. They had, for expansion of this new bridge, they had to remove all those pier column as well as the structural steel and build a brand new. We built actually 2 pier column. We have the 10 drill shaft, which contains of 6 pier column, 2 for the middle, 1 for the abutment, as well as 4 drill shaft for the wing wall. Total of 10 drill shaft, which was 6 feet in diameter and 34 to 40 feet in depth. We had 1 new abutment, we had 2 piers and 3 pier caps. The pier caps, as well as 2 structural steel, were fabricated or cast on site. And then in the Columbus Day of 2017, one weekend, we had to remove everything which was left from those existing pier cap, as well as the pier column and structural steel. We had to remove everything and we replaced, and we put all those pier cap that was cast in place on top of the new pier cap that we had, 2 pier cap in the middle of the whole bridge basically, as well as the structural steel. The 2 structural steel which was coming piece by piece from the Michelman in Pennsylvania, it was pre-assembled on the job site, and then in that famous Columbus Day, it was moved, shut down the whole area for 1 weekend, and with the SPMT self-propelled mobile transport containing 162 wheels, they had to place those pier cap as well as those 2 structural steel, basically, which contains actually girders, floor beam, deck plate, curb plate, side plate, and knee bracing. And we put the railroad back. And by the Monday of that week, the first train was crossing that bridge. So with that reason, we just expanded that area. We removed all the existing pier, and we put brand new piers, 2 brand new structural steel. And this way, we replaced that area for the Travis Spur Railroad Bridge. And I think there is a brief time lapse how we did that one. The contractor, KWM, had got 68 super foreman and all type of inspector, as well as a worker of different field, different expertise. KSE provided 12 inspector for duration around the clock for the whole weekend, and it was done successfully with no glitches, and everybody was satisfied with the performance of everybody involved. There's a time lapse on that one that we should be able to just see that one. You can see those operation was well coordinated with 2-3 different type of HORAM attached to the excavator. We had 2 huge crane, as was mentioned by James in the beginning of the introduction. There were 27 crane that contractor used through the construction of this project, and I had to review the calculation of those crane. I have to go do all the control checklist and send it back to Shapiro Associate, which was in basically construction of the crane in the whole tri-state and very well known. They have written specs on the crane, and if there was any comment I had to make sure that everything was taken care of before I submitted to the Port Authority for final admittance of the contractor bringing those crane to the job site and utilizing it for different tasks that they have. That was one of the things. I have to mention that, of course, as James was saying, for the whole entire job, we had 6,000 item of punch list. We have 3,300 of NCR, non-conformance report. And basically, I had to sign every segment of the job as a construction certificate, sign and seal with myself as well as the engineer in charge, and the contractor submitted to Port Authority. That's one of the responsibility. This bridge, which was built, it is, we call it the smart bridge. It contains a lot of characteristics that, as I mentioned here, like one of the things that is good to know about the structural health monitoring system. There are devices provided in the area of this bridge that reports and detect wind speed, wind gusts, the direction of the wind, temperature, bridge movement, different type of element of this bridge, which, as I said, structural steel, 8,000 ton of structural steel used on this project. Expansion of the tower, inclination, acceleration in case of earthquake. We had the ITS system for the whole job. Good feature for this project was the weigh in motion, which was provided on the approach slab on New Jersey as well as New York, where it would measure the weight of the vehicle, and if there is anything was overweight, the equipment itself would take a photograph, send it to the owner of that vehicle. We had traffic detection system, lane control system, roadway and weather. If it was a rainy day, basically, it gives you even the friction of the tire as well as the deck slab. They have traffic CCTV, they have variable speed sign, dynamic message sign, and SCADA system. And all this is controlled on 2 different rooms on either side of New York as well as New Jersey. and there is a control of the whole project, which is presently in the hands of the developer, which is underneath the New Jersey eastbound of the tower, which controls every movement of this bridge and every item that you can imagine, whether it is the fire detection location and electrical work and what have you. And all these over 150 cameras has been provided over the whole entire job. It's very secure and detect anything that you can imagine on this project. Next. Now we have to say that once the bridge was constructed, we had to remove the existing and demolish the old Goethals Bridge. For removal, since the design was lost in the 9/11 in World Trade Center, the contractor had to hire the R.E. Pearson, which is expert subcontractor in the demolition, and they had to do reverse engineering to find the member forces on this existing Goethals Bridge truss and try to find out a way to cut the main span as well as other stuff. So they had elaborate configuration on the main span, and finally it was cut. The piece of main span, which was weigh about 1,500 ton. Again, that was one weekend for 36 hours. With the cooperation of the Coast Guard, U.S. Coast Guard, as well as Army Corps of Engineers, we shut down the kill, and they had brought many barges lumped together and with the spot, so that they would bring this 1,500 ton main span truss of existing Goethals Bridge slowly, inch by inch, to sit on top of the barge and haul away to the north side, basically. And then the remaining of portion of the structural steel was cut by shear, by different type of cutting devices and lowered down. And of course, for that one, there must be some type of short clip that is going to be shown right now, and cut, and the pier column, existing pier column, was cut from the bottom of it and then pushed back with the attachment of Horam to the excavator, and you can see that one as well. This is the lowering of the main span, that 1,500 ton. It was done over 36 hours of the demolition of the first stage of demolition of the existing Goethals Bridge. As you can see, it was very elaborate operation. It was done successfully, and now it would show a little bit of the demolition of the approaches, structure, superstructure, as well as substructure of the existing Goethals Bridge. The pier column, typical pier column.